Thanks a lot, Stefan, for the warm welcome. So I'm Michael. I work on the V8 JavaScript virtual machine as well as the Blink rendering engine. And most notably, I work on garbage collection that is handled across both systems. And I'm leading the garbage collection efforts in the Blink rendering engine. So when Stefan asked me to give a talk about memory management and how all of this is tangled and how all of this works out, I looked at our work and thought, oh boy, it's really easy to get lost in very technical details. And don't get me wrong, I love this. But I also wanted to kind of zoom out a bit and provide a higher level overview of what's going on there, because I think it works really well for the web to expose JavaScript as a dynamic language, but the whole system underneath is C++ and is a static language. And I think connecting those is a problem that we have solved for now, but there is many systems out there that still struggle in getting this right. What you also can see here is an object graph. So when I started this work, it was very naive. I thought like I could get some insights into websites and what's going on there by just visualizing the graph a bit better and maybe diving into it and have a 3D model of those things. I quickly realized that graphs are insanely huge, super well connected, but we'll get to that a little bit later. So the work presented here is mostly done in collaboration with many Chromium teams, and specifically it's a collaboration with Ulan and Hannes, which are also working on the garbage collection team. And I think we have to also thank the more than 2 billion users of Chrome out there, because without those users, Chrome would probably not be a large-scale system that it is right now. And many interesting problems that we are working on only emerge because of software architecture decisions that we have taken in the past there. And without users, there wouldn't be all the need to optimize all of this and get it right. So what do we work on? I already said we're the garbage collection team, and I work on the garbage collection team. And we are in charge of memory management in Chrome's rendering engine, which is called Blink, and the JavaScript virtual machine called V8. This includes building tools to understand memory usage on the web, as well as redesigning architecture across different components, as well as integrating new algorithms and optimizations in those systems, but also benchmarking. So we essentially have a very broad stack that we work with to get memory management in the browser optimal. I think it makes sense to also look at how we operate, and the rule of thumb there is to have a bigger mission, but to make sure things ship and change incrementally. Chrome is moving insanely fast. There is hundreds of commits every day. It's very hard to maintain feature branches. So while that works locally for smaller changes, it's very hard to, for example, design a GC on the side in a different branch and then try to merge it back. So what we actually do is we try to develop a master and always keep backwards compatibility. And the fun story there is that when actually Blink switched over from WebKit's ref counting to having a tracing GC in C++, we had to annotate types with what their semantics were intended, with intended semantics. So all these types got like really long names because they would need to fit, they had to fit both systems for quite some time. So it's always important to keep a bigger mission in mind, and we are happy to change architecture, but it has to be in a backwards compatible way. Another example is that, and I will get to that, V8's concurrent marker, which was launched recently, was developed over a longer time, and initially only supported roughly 70% of objects. But we did already want to ship it because we wanted to get feedback from users and from user performance, and actually release the pressure of ourselves of actually shipping this thing. So it's important for us to get things out incrementally. And with Chrome being essentially in always release mode, there is a new release every 6 weeks. There is no time to rest, sit back, and take the whole system apart. So you have to think incrementally. Because it's essentially like changing the engine of an F1 car during the race. Having said that, We do follow the research literature around memory management, and dynamic languages quite closely. And every now and then we figure out, well, we can contribute something back. But also, what's also important for us is not just contributing back, but through writing things up, we actually discover where our systems, where they fall apart, essentially, because it's actually hard to write these things up. And every now and then we also discover bugs. So I would encourage everybody to, everybody working in industry still write their things up because it can help a lot. So this talk will mostly cover the recent publications. And to give you something to hold on to, I want to actually provide an overview of Chrome's architecture and how all these things sort of fit together, and then kind of cherry pick one example, because there are many examples of optimizations on JavaScript. I want to pick one of these optimizations, and then we can dive into that one and get a closer look of what's going on there. So zooming out completely, Chrome's architecture is based around processes. Everything is, we try to encapsulate things in a process that is running in a sandbox. On top of all of those things, there is an IPC layer that was developed for Chrome, but is now general purpose. It's called Mojo. And when you kick off some rendering, this was actually easy to explain in the past, because previously a tab roughly corresponded to a renderer. Then the web page, so the renderer gets a request for visualizing some resource, and then the whole rendering pipeline gets kicked off. These days, it's a little different. Renderers don't work per tabs, but they work per site, so to say, which is a concept that was developed in the past to securely isolate different domains and resources from each other. So a renderer actually might correspond to an iframe, and the browser may actually try to group many different iframes of similar domains into the same rendering process. For example, many Google products are shipped from the same domain. They are grouped into the same process because there is no security violation there. The browser may decide to put ads into some other process. So in practice these days, there is many different processes. They don't correspond to tabs, but different concepts. And data flow always goes through Mojo. There is no way to hold a direct reference into another renderer. From a memory management perspective, you can still obviously keep references alive by keeping so-called channels alive, but there is no way to directly access memory in a different process. Before we get to the interesting part where it all kind of connects, I think we should take a look at the rendering pipeline very briefly. I'm not a rendering expert myself, but I think it should be good enough to explain the pipeline on a very high level, and then see what's actually going on in the browser and where the interesting challenges arise. So at some point there is a vsync event or something similar, which essentially tells the rendering pipeline that a frame has been shown and we should compute a new frame. So what happens is that input events are processed, like touch, click, and click events. Callbacks are processed. For example, users can request callbacks whenever a frame is animated. It's called request animation callback. Or regular JavaScript execution happens. At some point, all this execution is done, and there is some state that it generated. And the state contains styles, and these styles are applied to generate a layout tree, which is the starting phase. The layout tree is then laid out, so objects are positioned in the layouting phase. A compositor is set up, kind of initializes a compositor which runs on a different thread for different layers that are then in the end put together. The paint phase translates still vectors or vector representations into actual paint commands, which are then rasterized for the GPU, so they are translated into tiles sent to the GPU, and the compositor puts everything back together. And then you get another vsync event that will tell you that you should compute the next frame. All of this should happen in 16 milliseconds, or users will notice a performance problem. So if you exceed that deadline, it will result in jank, which is a visual stutter. You can see it sometimes while you're scrolling that things kind of are a little janky on the web page. This is when we exceed this deadline. So looking at all of this, I think we can divide it into two stages that are interesting. So there is, let's start from the right side here actually. There is rendering, the whole rendering pipeline, which operates on C++. It's heavily optimized for performance. And I would say that most concepts are designed around performance, so it's not very, very easy to use. This rendering pipeline takes some input state we'll get to, and mostly, I would say, manages its memory locally, in the sense that after 1 or 2 frames, it's gone, and it's relatively easy timed, the memory. I think the interesting part here is on the left side, where we change some state, and I don't think it's not a secret, right? So the web operates in JavaScript. This is what we expose to the users, and the engine internally is C++. So at some point, there is some interaction between a dynamic language with semantics A and C++ with semantics B, and they may highly differ. This is also where interesting memory management problems come into play. So what is the state we are actually operating on, which is passed to the rendering pipeline at some point? It's called the DOM, which is Document Object Model. It's cross-platform language independent specification of HTML. There exists something that's called WebIDL, which translates interfaces into language implementations. In practice, though, that's almost always C++ because all major browsers use C++ rendering engines. So you have an abstract specification which gets translated into C++ classes that are read by the rendering pipeline. The interesting part here, I think, is that they are translated in a way so that the rendering pipeline can actually easily read them. So it's optimized for reading. And then there is JavaScript, language of the web. So I'm leaving aside WebAssembly here because it also has its space in this whole web universe. But for most parts, if you have applications these days, imagine your favorite news website or social network, these are written in JavaScript. And they use JavaScript to interact with the DOM. We don't need to be experts on JavaScript. This is a very simple function that creates one div element. And I think interesting here, and we'll get to that in a bit, is that there is some concepts that are JavaScript, that are part of the language, but there is also concepts that are part of the DOM, which this append child function here, for example, which is not implemented in V8, the JavaScript engine, but it is implemented in the renderer. All of this, though, is executed in a virtual machine because we don't trust this code. So for the rest of the talk, we'll actually have a look at Blink and how it integrates with V8 and how it changes state there. And I think the next interesting piece here is that there is this so-called bindings layer, which glues V8 to Blink. So for most parts, the Blink rendering engine doesn't know about JavaScript. It knows about its C++ objects, and developers in the DOM, or people that write specs and then implement features, they only know about their C++ objects and don't have to deal with JavaScript. So because most of the connections are established on the bindings layer. And V8, for architectural purposes, actually has a hard API boundary, which comes with benefits and drawbacks. I would say like there is an obvious benefit of having like clear encapsulation of ECMAScript in V8. It also allows us to embed or provide V8 to different products, which is great for adoption. It comes with the problem that it's often hard to properly integrate into this bindings layer because we need to find proper terminology and abstractions to actually connect those. So taking a step back, when I started working on this problem of how to do memory management across these boundaries a few years ago now, we looked at systems in general and looked at how they are designed. And we looked at VMs and how they attach to other environments. And it became clear that there is actually a problem because also in Chrome you can see that people and teams work in their components and they care about their components and they hardly ever zoom out and see the bigger picture. So what can happen actually is that you have a component, works nicely in isolation, but there is ways to reference some other component. And from perspective of the component A here, anything that's incoming, whatever memory management system you use, you treat it as root. And obviously, you can play this trick vice versa. And what happens then is that you end up with reference cycles. And there is tons of literature out there that tells you how to break those, how to use tracing GCs, how to use weak references, how to manually break them up using explicit events or to do cycle detection. But in practice, what happens is that nobody, or this hardly ever gets applied. It gets applied in web browsers because they're forced to. But if you look at other systems and how they provide their VMs, it hardly ever is a problem statement. So I want to post it actually here. Coming back to V8 and Blink, I think it should be pretty obvious that we have this problem. So JavaScript and the DOM is somehow connected. And what actually happens, or what the architecture actually looks like, is that objects for us come in halves. So as soon as you parse a document, you obviously get a representation in C++ because that's what you want to render. So as soon as you parse a document, you get a document object. And this document object implements the web spec. There is a DOM specification, and that tells us what kind of methodologies it needs to implement. There is also a JavaScript world as soon as you access it from JavaScript, which is solely used for JavaScript semantics. So when you think about concepts such as properties, elements, functions, like closures, code, and whatnot, all these things are encapsulated on the left side. But on the right side, we have the DOM specification. They need to reference each other simply because they need to delegate when we request certain features. So you write JavaScript, but you may request a DOM operation. So you need to find the corresponding DOM element so you have this reference. And vice versa, callbacks get executed that do certain things. And so we create these pairs of objects. And whenever you reference something in JavaScript that looks like that, you actually create this pair. Now, you could argue, well, that's all very complicated. Is it actually a problem in practice? And I think to answer that question, I want to just give one example which should highlight what's going on. You may still have the argument of, well, you can use weak references here or there. You can try to get something like static ownership working. I think we should have a look at this example, and then we'll see why that doesn't work. And what we're mixing here is server-side and client-side rendering. What this means is that some things are rendered on the server, meaning that the server actually provides a response with DOM elements already. And some things are rendered on the client, meaning that we actually create things on the client dynamically. So let's walk through this and see what happens to the object graph. And I think then things become pretty clear. The parser sees a document, creates a document object. For the purpose of this example, we simplify this whole system a lot. So we do sequential parsing, sequential compilation. And we compile this function to some code. Might be some bytecode that can be interpreted, might be native code that can be run directly on the CPU. So we create this code object. We then want to attach an event listener that runs when the document is fully loaded. So we request document, which gives us our first pair here. We then use that document to actually refer to the DOM and add an event listener, which creates an object structure on the DOM, because event listener is a concept of the DOM and doesn't exist in JavaScript. For that purpose, we also need to create a JavaScript function object, which is pointing to that code. And on the C++ side, we have some concept like event listeners and strings and so on, and some way to map them. We then continue, create a body element. We create a span element, and then we are done with our parsing. So we can actually invoke that event, and we actually will execute the code, which will create us a new diff element, which we refer to from JavaScript. Document we already have, but we're accessing body as well. And then finally, we are appending the child, and we have our final graph here. I think this should give an intuition of what's going on the web with respect to objects. And I think when I first looked at this, it was not really clear where to draw this boundary. Obviously, we are splitting it in half, but it's often not clear where concepts are implemented. And in fact, there was an experiment in the past that tried to shift this boundary here a little, in the sense that people tried to implement parts of the DOM specification in JavaScript, which would simplify this problem, right? Because you shift this boundary into something that may then become trivial. That didn't work, though, back then because the language wasn't there. It also didn't work because the renderer wants fast access on the DOM, so we have to keep that boundary. And I think from that one, it's pretty clear that all these ownership relations are dynamic. You can have arbitrary references into both directions as well, in addition to those pairs. So there is no way we can easily break up cycles. And I think it's easy to imagine what modern frameworks will do to your object graphs. Imagine your favorite news website with a paywall in front that tries to track and figure out things, or a social network that tries to figure out and adopt based on your needs, searches, whatnot. So we took a step back and thought, like, well, actually, what we just did is we tried to shift the boundary left and right, which is essentially zooming out and pretending it's one system, which is what we proposed with our cross-component garbage collection approach, and which was presented at UPSLA last year. The long story short is that essentially we propose a mechanism that is language independent for garbage collection purposes. As soon as you decide you can stick with tracing garbage collection, you can actually just pretend this whole system is one garbage collected system, and you can compute one transitive closure of live objects and figure out which objects are live and which objects are dead. And for that, we introduced in Chrome renderer garbage collections, which start at C++ and JavaScript roots, and then at the component boundary delegate to specialized garbage collectors. The interesting observation here is that if you maintain a set of invariants in both systems, you can actually then still specialize your GCs to the needs of the language. And we'll get to one example later on, which is specialized to JavaScript semantics and the JavaScript object model, which would not work in C++. Before we continue, let's briefly get us up to speed on basic garbage collection terminology. We use tree color marking across all the code bases, which essentially means that in order to figure out live objects, we pretend all objects are initially white and not discovered. We started a set of roots. Gray, when we discover an object that is not yet processed, we push it on some working list, abstract working list, whatever it is, and we color it gray. Which indicates that there is more work to do. Once they're fully processed, they're black, they become black, and objects that remain white at the end of the garbage collection phase are then reclaimed by the garbage collector in the so-called sweeping phase. So how does it look like on our example? We pretend that there is a root somewhere into the document. We figure out document is live, and at this point we actually delegate over to a different GC, which knows a different object model, but which knows how to deal with C++ objects. Once we are there, we actually continue in both components because they can be treated independently. The example doesn't show that here because it was hard to generate, but graphs are usually well connected. So what happens is that once you pass a few references left and right, both GCs or both tracing systems can continue independently. This works well for JavaScript and for the DOM. Maybe a little bit tricky to get right in or get performant in systems where where graphs are not that well connected. So then we can continue on with our tree color marking. When we discover a reference that we can pass back to the other GC, we do that, and then at some point we figure out all the live objects. There is a fixed point where we bounce between both GCs in an atomic phase that also handles special objects like ephemerons, which exist in JavaScript. And then we can finally reclaim any objects that we haven't reached through this phase. Important here is that the GCs actually can branch off in their own implementations because they can do different things then. From a tooling perspective, we basically provide a few things in both worlds. We provide identity, that's kind of necessary. We provide naming, so every object has a name, even though that name, and I will get to it in a second, is not always fully useful. And there is ways to get edges from objects, which is also what the GCs use to dispatch in their specific worlds. So what you see here is actually dev tools on an example where we investigate a memory leak, which conveniently is named leak. And once we found that class, we actually want to see where it's retained. And we see that it's retained somewhere on the window object. What we don't see here is that actually we are crossing component boundary multiple times. So some of these objects exist in JavaScript and some in C++. Because there is many C++ objects, a few thousand actually, we don't give all of them a distinct name. And for those that are not important, we just give them a name that's called internal node. That's what you see here. For users, it shouldn't, or our users are web developers in this case, it should not really matter where these objects live, because they're mostly interested in the retaining path, and there is usually interesting stuff on the top and on the bottom, which they can influence. And what I think we have established now is a system where we essentially have a GC system in the renderer where it doesn't depend on where objects reside. And I think it's now a good time to look at the V8 and Blink garbage collection architecture, because this illustrates that these systems are vastly different. And they have this one common link, which is a tracing GC, which they use to collect garbage in the whole renderer. But they have their own optimizations that are very customized to their own needs. For example, V8 has a generational garbage collector with a young generation that's a semi-space copy, which we call scavenger. It's completely independent. V8 has a few optimizations with respect to allocation, so it folds and pretentious allocations. Blink has optimizations where it knows that it can explicitly free backing stores on clearing of an array, for example. There are some things that look very similar, for example, concurrent sweeping, that have vastly different implementations. V8's object model doesn't usually have finalizers. So for V8, concurrent sweeping can be actually mostly concurrent because most objects don't need main thread interaction. So there is actually concurrent helper threads that can process most of the work there. For Blink, because we are in C++ world, we have to deal with finalizers. And because of the way how Blink evolved from WebKit, we actually have to process finalizers on a specific thread. So there is concurrent sweeping in Blink, but it has dependencies on the main thread, which are C++ specific and only apply to that world. There would be many topics we could go into now. Like all of those have their own semantics and constraints, and I think it's pretty interesting. Let's pick concurrent marking in V8 because it was one of the most recent things, and it was one of the things we worked relatively long on, and it was hard to get into V8. So I will get into what shape changes are in a bit. If you are interested in the details, please check out the ISMM talk by Ulan and check out the paper. The motivation here is relatively simple. JavaScript is becoming more and more popular, and in fact, we are seeing websites that ship applications that have even gigabytes of live memory, which results of seconds of marking time on the main thread, which even though it can be, we already have an incremental system for many years, it doesn't solve the throughput problem. There is always problems with the GC trying to keep up with an application that allocates like crazy, and a way to solve that is through concurrently processing objects. And we realize that even on low-end devices, you usually have more than one core available these days, which you should probably utilize to unblock the main thread. Our problem? We did a lot of research on traditional literature, and we figured out it doesn't cover shape-changing objects. And we'll get to the problem now. Before that, let's give a quick recap of dynamic languages. I think it's pretty common, should be pretty common knowledge here. But these languages mostly use some hidden class representation in the back, which they try to optimize and get the best representation for, to optimize access and usage of the actual object. So V8 uses its first word, its header word, to point to a hidden class, which represents type, size, and layout. This is a regular object, so it points to the meta hidden class, and I haven't put that arrow here, but this one actually points to itself. In V8, words can have different types. We call them field types. And those can either be tagged or untagged, where tagged means it's either a reference or an unboxed integer, or it's raw bytes, and its semantics depend on the actual usage. We use value tagging on those things to differentiate between integers and references. So the last bit will tell you whether you're dealing with an integer, which is in fact a small integer because it's limited in bits, right? Or whether you're dealing with a reference to an actual object. And together with your hidden class, you can always answer the question, hey, I have an object O with a specific hidden class, and I have offsets in there. And then you can answer the question whether offset 2 is a SMI, is a reference, or whether it's raw bytes. Which already gets me to an interesting optimization, which V8 uses for high performance. And I have to make clear here that I'm simplifying this a bit. This example works for our purposes and works to represent what kind of thing can go on in V8. But in practice, it's more complicated, and you need more JavaScript voodoo to actually trigger those transitions. But in theory, we could make the VM trigger them even in this example. So we create an object point here, which points to a hidden class. It's empty hidden class. This one is actually canonicalized. It doesn't matter too much here. V8 has properties and elements backing stores, which are generic concepts used for, if an array is used as array, we have an elements backing store with a very dense representation. If you attach properties to an object, you, in the very generic case, have a properties backing store, which is a hash map. We also have space for in-object properties, and V8 uses so-called slack tracking to figure out what the shape of an object should be. Initially in JavaScript, there is class declarations now, but they didn't exist back then. So what you have actually at this point is an object point, and you don't know what it's used for. Does it get a name? Does it coordinates? How many does it get? Nobody knows. So we reserve some space in a Slack area. And actually, once you get to assigning the property X, you use a little bit of that Slack area. And you create an object there, which represents the double. You don't know better. At some point, you realize, though, that, well, actually, after many instantiations, the point always just has an X. And the X is just a double. It's never used like anything else. So yeah, you actually can transition to a different hidden class that inlines the double there. And if you would then assign some string to X, it would actually fail because, and it would transition into another hidden class which generalizes the property again. What's actually missing here is that at some point the Slack area is completely removed. So we consider objects as being stable and actually need to do full transitions to new types when they change. So what you can see here is that the VM may change the representation of an object, may do so even in place on the already existing object through certain optimizations. And I think it already is clear now that at some point we treat it as a reference, and at some point we treat it as raw bytes, which we know should be a double. So let's do some more GC intro to get us to the problem there. When we visit an object, and that's how traditional literature proposes it, even in concurrent settings, you somehow store the color black in your mark bits. We won't go into the memory model details there. We can discuss that offline. You need to load a class, and you at some point need to iterate all these tagged fields if you put it in V8 terminology. And for each tagged field, you need to load the reference and follow the reference, where following a reference means checking the tag and then trying to transition it to the color gray and putting it on a work list. In addition, which will be important just in a second, we maintain a strong tree color invariant in V8, which means we don't want black to white references. So we issue write barriers after each store. The write barrier essentially checks whether the value has a ref tag, and if marking is on, it also pushes the object. There exist multiple versions of write barriers. We use this one consistently across Blink and V8, which gives us a few nice guarantees there, and a few ones, which we'll see in a few slides, we can actually not use because we reuse the mark bits for something else as well. And then we have to distinguish now. There exist safe shape changes and unsafe shape changes. Safe shape changes we can actually handle with traditional marking. For example, the algorithms I showed you are able to handle appending a field, even in a dynamic object. Because the GC will either see the old version of a class where the field is not there and the write barrier will handle the case, or it will see the new version of the class where the reference is there and it will see it through that reference. There is unsafe shape changes though, and they usually require special handling. Unboxing doubles is one of those things, and it usually unsafe means that the representation of the underlying raw field for us is changed. In the paper, we establish a few more invariants, one of which we call a reference safety, which is important for us. And it essentially says that the value to pass to follow reference should be a tagged value at all times. And this is where it obviously breaks. If you have a concurrent marker that runs on a helper thread, and your main thread is changing the type of an object, the tagged fields may change. So what the concurrent marker may see as tagged value may already be written as raw bytes in our double unboxing scenario. Literature actually suggests a few things there, which actually come out of this community or Splash in general. They're called layout locks. They exist in light and regular versions, and depending on the VMs, people have tried to optimize those. I think simplified, if we want to visualize it simplified, it just means locking the object while doing the layout change. And the different versions of layout locks try to optimize when these locks are taken, so they bail out in fast cases. What V8 uses and what we have come up with is actually a little bit different. It's a wait-free snapshotting algorithm. And I will walk you now through this algorithm to see what's going on there. When we do an unsafe layout change in V8, what we actually try to do when marking is on, we try to first migrate the mark bit first to gray and then actually migrate it to black, essentially getting exclusive access on the object. If that transition from gray to black is successful, then we will actually visit the object and do the unsafe layout change. We are guaranteed, because of that transition, that the marker will not see that object. On the marker, on the other side, we actually first take a raceful snapshot based on an existing map that we read. So we read the map, take a snapshot of all tagged fields in that map. We then try to transition the object to black, and only if we succeed, we go through the snapshot and follow the references. At this point, we are guaranteed that we had taken a good snapshot that the GC can work on. And because the unsafe change on the mutator thread will actually do a write barrier as well, there is no problem there. We then compared in Chrome M72 based on Chrome's benchmarking framework that is a record replay framework on real web pages. We compared several different configurations. And our baseline here was the configuration with incremental marking. We implemented a configuration that just works on traditional marking as well, and we implemented snapshotting and locking based on words and pages. What's interesting here is that, so for Chrome, maybe a little bit different, and JavaScript in general, maybe different from your dynamic language that you care about, but for Chrome, the main thread performance is the relevant thing. So we actually care mostly about how JavaScript executes and blocks execution on the main thread. And here it turns out that all these configurations perform, I would say, roughly equally well. So what you see here is actually on the y-axis, you see a comparison to the baseline configuration. And on the x-axis, you see the different configurations. And we use a Wilcoxon rank sum test to actually determine whether our results are significant or not. The white box shows a significant improvement here. So what we see is that all these implementations with respect to main thread performance roughly perform the same. There is differences, obviously, but I think you would probably be happy with either of those implementations. What you don't see here is that the N version, for example, that's the version that uses traditional marking but doesn't do some optimizations. It heavily regresses on some benchmarks that users also care about. So we cannot use that in practice. Then we looked at total marking time, which is essentially marking time on the main thread plus marking time on all helper threads together. Compared to baseline again, Wilcoxon rank sum test. And again, on the y-axis, we show improvement or regression, and on the x-axis, the configurations. And we see that actually the snapshotting version performs best here. For us, it is intuitive that on general, we regress performance here with respect to total marking time because there is synchronization involved. But we are very happy with where the snapshotting brought us. So to conclude this paper here, I think our observations were that shape changes may appear in your sequential VM without concurrent GC. And there exist unsafe and safe shape changes. There is more in the paper on that, where we classify which shape changes we consider as safe and which ones we consider as unsafe. Safe shape changes can be handled by traditional marking, and you should probably do that if your language falls into that category. Unsafe shape changes require special handling and can use locking or our proposed snapshotting algorithm. And having said that, I actually think it's a nice picture which we can round up, and I want to give two final thoughts here that kind of have emerged over the last years that we've been working on these systems. The first one is related to our general architecture with bindings and different environments. And we think it can be, or it is a real problem in practice. There is more middleware frameworks out there that suffer from this problem without realizing what exactly their problem is, but they encounter it left and right, and lack of a proper solution. Browsers, I think, are in a relatively good shape because they have figured out their constraints and environments, and they have to deal with this problem from the beginning on, essentially. For Chrome, we decided it was a viable option to put a GC on top of it and essentially maintain two specialized GC versions that can work together. I think for other environments, you should probably try to restrict your system first and restrict the concepts you expose on your APIs. And if you can get away with that, it's probably a more lightweight option. For Chrome, we definitely have the engineering power, and we have the people to maintain these two GC implementations, and we also are able to maintain special systems that either deal with C++ or JavaScript. But even in Chrome, we are already searching for ways to minimize the duplication there and try to use as much shared code as possible and shared concepts as possible. And the other thing is when we introduced concurrent GC, or over the years, we actually introduced many concurrent concepts into V8. And we realized that potentially, I mean, that's a very, very broad statement, but we realize very well when you start a VM from scratch, you care about sequential performance most. But you should, if you ever have the plan to actually make it a mature production VM that should be used by industry, you should probably care about concurrency as well. And you should incorporate it in your design phase. Otherwise, you may be surprised by a lot of invariants or a lot of concepts that you cannot deal with when you try to introduce a concurrent GC. Just to give you a number here, V8's concurrent marker was put on the table many years ago, and it took years to actually figure out how to properly fit it in the system, what we can change, what the runtime needs to maintain for peak performance. And so this was a very, very long process. For Chrome, we decided, well, the user base is large. It's immense. There is many, many different usage scenarios. And one of these usage scenarios is peak performance, sequential peak performance. So we cannot regress this one when we are taking the complexity hit of providing a concurrent GC implementation that can even work with those. But we would suggest that people figure out whether they need that complexity for their system. Having said that, thanks for your attention, and I'm happy to take any questions that may have come up.
Thank you, Michael. We have plenty of time for questions. Maybe I start with a question.
Okay.
I just have, it's more a detail.
Yes.
In how you measure the performance in
Yes.
the graphs. You were talking about total time.
Yes.
And it seemed to me that that meant the sum of all of your CPU times for the different worker threads.
Yes.
That seems to be a measure where you're interested in sort of the power that you're using.
Yes.
And not so much the responsiveness.
Yes, exactly.
And initially in your talk, you were mostly interested in responsiveness, vsyncs and all of this.
Right. So the question, I guess, is, or the comment is that most of the talk is around latency and jank critical use cases, whereas one of the slides was showing something that more relates to power. So to relate that a bit, we are mostly interested in jank, which is this kind of picture. This is the highest priority for us. But it turns out that on low-end phones, battery is important as well. And we need to we are prioritizing it accordingly, but we care about it as well. These are two graphs. The paper presents many more. I just wanted to show a picture here how these implementations, because from a main thread performance, it looks like they are roughly the same, so we could go with either way, whatever is simplest, essentially. But if we care about power, there are differences. This is the thing.
My